In this supplementary video, I'd like to continue our discussion of number systems by introducing you guys to a very cool four-dimensional number system called the Quaternions. As a review of what we did last time, what we did is construct the set of complex numbers from the set of real numbers simply by taking ordered pairs of real numbers and then setting up addition and multiplication operations. And what we discovered when we examined complex number multiplication is that this operation very nicely encodes rotations in 2 dimensions. A very natural question to ask at this point is there another number system which will take care of rotations in 3 dimensions? And the primary name associated with this so-called rotational problem is William Hamilton. This is the same Hamilton who got his name on the Hamiltonian operator in physics. His primary insight is that instead of considering 3-dimensional numbers, that would be the most natural answer. We had a 2-dimensional vector and the complex numbers taking care of 2-dimensional rotations, so why not consider a 3-dimensional vector taking care of 3-dimensional rotations? His insight was that we should consider not 3-dimensional numbers, but 4-dimensional numbers. That is, we're going to consider objects within R4. And instead of having one imaginary unit, which would be I in the complex numbers, we should have 3 imaginary units, I, j, and k. Now remember, in the complex numbers, the fundamental equation with I was that I squared be equal to -1. And Hamilton's insight was that these 3 imaginary units should be related in the following way. That I squared, j squared, and k squared, very similar to the complex numbers, these should be equal to -1. And furthermore, this additional relation that ijk should also be equal to -1. And this is really the fundamental equation which is going to set up Quaternion multiplication. Now, what did these numbers look like? Well, the complex numbers were written in the form a plus bi, where we had some real part here, we call this the real part, and then the imaginary part here, just a plus bi, or in ordered pair notation, just ab. Now the Quaternions are going to have 4 parts to them. We still have these coefficients a, b, c, but now we have d because we're doing a 4-dimensional vector here. We have these 3 imaginary parts here, whose coefficients are b, c, and d, and we have this so-called scalar part. In physics, one often says that this is the scalar part, and then this coupling of b, c, and d is a vector part. But here we can see this is an ordered 4-tuple, or ordered quadruple. So this is going to be the primary way that we're going to write the Quaternions, as an ordered quadruple. As with the definition of the complex numbers, the definition for the set of Quaternions, which we're going to denote by the capital H, H standing for Hamilton, is quite simple. In fact, what we're going to do is just pick out any 4 real numbers and then form a ordered quadruple from them. So what we're doing is we're selecting members from r times r times r times r, where the times just means Cartesian product. And again, we often denote this as R4. Just as complex numbers were R2, the set of Quaternions is going to be R4. So the definition is quite simple. And as I said before, we may often convert between notations. For complex numbers, instead of writing 1, 2, I might denote this as 1 plus 2i, and vice versa. I might write 1 plus 2i, but we might write this as 1, 2 as well. For the Quaternions, we might go back and forth between writing 1, 2, 3, 4 as an ordered quadruple, and writing 1 plus 2i plus 3j plus 4k. And again, this first entry here, the 1, is often called the scalar part, and then this ordered triple consisting of the last 3 entries is sometimes called the vector part. And as with the complex numbers, we set up the definition of what the set is, and now let's consider the algebra behind computing with Quaternions. Now let's start with Quaternion addition. Now addition is going to be fairly simple, and it's just like the complex numbers. This is going to be simple vector addition, adding component-wise. That is, if I have 2 Quaternions, let's say I have 1, 2, 3, 4, or 1 plus 2i plus 3j plus 4k. And I have another quaternion, which is going to be 0, 0, 1, 1, or just j plus k. I add component-wise. I add the scalar parts to each other, so I get 1 plus 0, that's 1. I add the i's together, that's 2 plus 0, that's 2. Add the j's, 3 plus 1 is 4, and then the k's. 4 plus 1 is 5. So you just add like you would normally add vectors. And in general, if I had two quaternions, let's say A, B, C, D, and another one E, F, G, H, then just adding the components, I get the third quaternion, the output quaternion, as AE, BF, B plus F, C plus G, and D plus H. So just simple vector addition. And just to put this once more in notation, in the ordered quadruple notation, I have A, B, C, D, and E, F, G, H, and the result of quaternion addition is going to be A plus E, B plus F, C plus G, and D plus H. Quite simple. And as before, we want to examine some of the algebraic properties. We see that quaternion addition is closed. When I add two quaternions, I produce another quaternion. And just like complex number addition, quaternion addition is commutative and associative. And these are very easily proven. What is the additive identity for the quaternions? So again, I'm looking for the quaternion such that when it's added to some other quaternion, let's say ABCD, what I get out of that is ABCD. And that's pretty obviously going to be this quaternion, the 0 quaternion, which is going to be 0, 0, 0, 0. And also the additive inverse. Here I'm looking for the quaternion such that when it's added to, let's say, ABCD, gives me the additive identity, or 0, 0, 0, 0. And here that's just going to be the negation of ABCD, where I negate all the components. So the additive inverse of ABCD is just minus A, minus B, minus C, minus D. So now let's set up quaternion multiplication. And we're going to take a similar strategy as we did with the complex numbers. For the complex numbers, we just multiplied A plus BI with some other complex number, C plus DI, in the usual way, and then we just used that algebraic property that I squared should be equal to minus 1 to discover how to multiply complex numbers. Now we're going to do the same thing with quaternions, but when we do this, when we distribute, we're going to start to get terms like I times J, J times I, K times I, and a few other possibilities. So we're going to need to know what to do with IJ and JI, and so on. And just as we used for the complex numbers, we used I squared equals minus 1. The fundamental equation that we're going to use in terms of setting out the algebra is this one, this fundamental equation of quaternions. So what we're going to set up, just to keep this clean, is we're going to set up a multiplication table between ij and k, where on this column here is going to be the symbol on the left-hand side, and on the row it's going to be a symbol on the right-hand side. For example, if I want to look up what ij is, I look up I, and I go over to j here, so when I discover what ij is, I'm going to write that here. And if I want to know what ji is, I go to j, and then I here, and I'm going to write that there. So what we need to do is fill out this multiplication table. And just from the fundamental equation that I squared, j squared, and k squared should all be minus 1, I've already written minus 1 on this diagonal here. And the equation that's going to allow us to discover what the remaining entries are is going to be this one, ijk equals minus 1. So let's derive the remaining entries on this table. Down below, I've completed this multiplication table, but we're going to go through each of the remaining 6 cases to show you why it is that, for example, ij is going to be equal to k, and so on. So the rest of the 6 entries are going to be derived just by playing around with this equation, ijk is equal to minus 1. And one additional note before we get started with the derivations is that we have to be extremely careful to not commute, because we don't yet know that quaternion multiplication is commutative. And in fact, it's going to turn out that it's not commutative, so we have to be careful of that. So we're going to start with ijk is equal to minus 1. What I'm going to do here is multiply on the right by k. So I'm going to get ij, k squared is equal to minus k. And that since k squared is minus 1, I get minus ij is equal to minus k, which says that ij is equal to k. And then let's derive another one. Now I'm going to take this equation, I'm going to multiply on the left by I, So I'm going to get I squared j is equal to ik. Again, I squared is equal to minus 1. So I get minus j is equal to ik. So that gives me that entry right there, that ik is equal to minus j. And let's derive another one. So we start with ijk is equal to minus 1. Now I'm going to multiply on the left by I. So I get I squared jk is equal to minus I. I squared is minus 1 again, so minus jk is equal to minus I. So that tells me that jk is equal to I. So that gives me that one there. So I've already completed this upper triangular portion of the table. And then we've got 3 more to derive. So now I'm going to start with jk is equal to I. I'm going to multiply on the left by j. So I get j squared k is equal to ji. J squared is equal to minus 1, so I get minus k is equal to ji. So ji is equal to minus k. And notice one observation we can make already is that we notice that ij is equal to k. Notice that when we commute those two, we get the opposite of that one. ij is equal to k, and now ji, the commuted version, is equal to minus k. And just as a spoiler alert, this is going to appear for the rest of them. But let's continue with this. We start with ji is equal to minus k, what we just derived. We're going to multiply on the right by I. So I have ji squared is equal to minus ki, which gives me minus j is equal to minus ki, or j is equal to ki. So where's that? Ki is equal to j. And just as before, when we commute, we discovered before that ik is equal to minus j. And we found here that ki is equal to j. Again, we have that observation that when we commute, we can just add the minus sign while we're working with these 3 imaginary units. And the last one, we start with ki is equal to j. We multiply on the left by k, so I get k squared I equals kj. K squared is minus 1, so I get minus I is equal to kj. So that gives me that last entry here. And again, I see that the kj is minus I, and over here I derived the jk, the commuted version, is equal to I. So this is the completed version for working with these imaginary units. And really only notice that, let's say you really had to memorize these things. You really only need to know 3 of them. And then remember that when you switch the order, you just add a minus sign. So what you would have to know is that I times j is equal to k. A nice one to know is that ki is equal to j. And then the jk is I. Those are the positive ones. Then when you switch the order, then you just add a negative sign. Before continuing, I'd like to make one observation related to how physicists treat these units I, j, and k. Now, if you've taken physics, you might instinctually associate I, j, and k to the x, y, and z directions. And historically, this is how it was all set up through Quaternions. And you may also realize that if you do that, if I associate I to the x direction and let's say j to the y direction, then I times j being equal to k, the z direction, is very, very similar to saying that x cross y, taking the cross product between the unit x direction and the unit y direction, gives me the unit z direction. So if you've seen any physics, this is actually very much tied in to the cross product operator. That when you do something like ij, when you do x cross y, you get z. And if you flip that order, if you do y cross x, you get negative z. And continuing with the other unit directions, if you take, let's say, j times k, which would be similar to saying y cross z, you get x. And historically, this is really where the cross product comes from. It's not so much that we see this and we interpret it as a cross product. We don't say that this is a special case of the cross product. Historically, what happened is that Quaternion operations were developed, and then we sort of abstract the cross product from these particular operations. So that's just one interesting note if you're interested in physics. Now that we know what to do when multiplying these imaginary units, and we have the multiplication table, we're now prepared to set up quaternion multiplication. So I'm going to do precisely what I suggested before. I have two quaternions, A, B, C, D, and E, F, G, H, and I'm going to just multiply them, just distribute all the stuff. Now, as a warning, the next few minutes are going to be quite messy in terms of distributing all this stuff. But after we get through the mess, we're going to clean it up quite quickly. So you should just stick through with this stuff. So first I'm going to distribute the A to all these terms here. So I get AE plus AFI plus AGJ plus AHK as my first collection of 4 terms. And just for clarity, I write in bold these imaginary units. And then I'm going to take the BI and I'm going to distribute to all this stuff here. So I get BEI plus BFI squared plus BGIJ plus BHIK. And I distribute the CJ to all of these 4, and I get the following. And I don't have to read that to you, you can read that yourself. And then lastly, I distribute the DK to each of these 4 elements, and I get the following. And notice now I'm getting these products of imaginary units like IJ and JK and KJ, but I now know what to do with these. And I'm going to simplify these expressions line by line. So let me deal with this first line. And you notice there's nothing we can really do. We just have I, J's, and K's here. Let's move on to the second line here. I noticed I have an I squared, so I just replace that with a -1. The IJ gets replaced with a K. IK goes to -J. And then the coefficients are unchanged, except if you put a negative sign. The third line, J goes to J. JI goes to -K. J squared goes to -1. JK goes to I. And then the fourth line, K is unchanged. Ki goes to J. Kj goes to -I. And K squared goes to -1. And that really completes the simplification. Now what I'm going to do is group all of the common elements together. First, I group all of the scalar elements together. So I'm going to group AE with -BF, -CG, and -DH. I'm going to write that here as the first element of my new quaternion. And then I group all the stuff containing an I within. So I'm going to group that with that, that, and that. And then I group the J's together. Be 1, 2, 3, 4 terms. And then the K's together. So I have 1, 2, 3, 4 terms there. So I just group all this stuff together that has that imaginary unit in common. And now I finally define what's called the Hamilton product, which is precisely what we've done. The Hamilton product is just the quaternion multiplication. That the quaternion product between ABCD and EFGH is going to be the following. And that's precisely what I just derived in the previous slide, where this is going to be the scalar part here. This is going to be the I component, the J component, and then the K component here. And this is really as messy as it gets. And it's really not much messier than, let's say, if you know anything about the cross product, it's really not much messier. Now that we've defined quaternion multiplication, or the Hamilton product, let's clean this up a bit so that we can very nicely do computations with quaternions. In fact, what we're going to do is we're going to set up a matrix, which is going to correspond to a quaternion. And that's really what's going to keep these computations clean. So what I'm going to do is I've written each of these 4 components of the new quaternion in such a way as to have some coefficient times E, something times F, something times G, and then something times H, in that order. I have EFGH, EFGH, and EFGH. Now let me write that vertically. So this first line here is going to be just that first component of the new quaternion. And then I'm going to write the second, third, and fourth below it. And notice that all the E's line up in a column, F's line up, the G's line up, and the H's all line up. So I've just commuted all of the stuff so that this would happen, that E's line up, the F's line up, the G's, and the H's all line up with each other. Now what this very naturally suggests when I write it like this is that I can write a matrix which will correspond to doing this operation. And since the EFGH is repeated in each line, the vector, this suggests that I should write the vector EFGH and multiply on the left by some coefficient matrix. So it turns out that I can write this linear system in the following way, where I have a 4x4 matrix on the left here, which is just writing out all of these coefficients, like a minus b minus c minus z, which is this first line here, and then so on. And I take that 4x4 matrix, and I multiply on the right by e, f, g, h. And what I get as a result is going to be another four-dimensional vector, which is going to be precisely the result of that quaternion multiplication between a, b, c, d, and e, f, g, h. So let's say you had to really memorize something. In my opinion, it would be the best idea to memorize this matrix here instead of remembering all these different combinations of a's and e's and d's and g's. This is just a mess here. But this matrix is actually very symmetric, and this is actually very easy to memorize if you were forced to do something like this. So for the rest of this video, we're really going to work with analyzing the properties of this matrix. Now, quaternion multiplication isn't usually presented in this fashion, but in my opinion, this is much easier to analyze because a lot of questions about quaternions and multiplication of quaternions just become questions about multiplying matrices. In the case of quaternions, these are very special 4x4 matrices, and these are much easier to analyze in my opinion. And notice that this 4x4 matrix is quite special looking because this real component, the so-called real or the scalar component, is right along this diagonal here. All these a's are along the diagonal. And furthermore, that if I take some element here, let's say in this triangle here, in the upper triangular portion, that when I flip it over the diagonal, I just have to negate that entry to get the corresponding entry here. For example, if I take this minus c here and I reflect it over the diagonal, it's just c over here. Or if I take this c over here, I reflect over diagonal, it becomes minus c. So this matrix is almost what we call skew symmetric, which means that when we flip stuff over the diagonal, that's the same thing as negating it. But it's not quite skew symmetric because the diagonal entries here are non-zero. But this matrix is very, very symmetric. It's very, very easy to remember as opposed to this nasty formula here. As with addition, let's talk a little bit about the algebraic properties of quaternion multiplication. Now, we've seen that quaternion multiplication is not commutative. That is, we've seen many counterexamples already. We saw that ij is certainly not equal to ji. And in general, quaternion multiplication will not commute if you pick other quaternions to multiply, for the same reason that matrix multiplication is almost never commutative. However, just like matrix multiplication, quaternion multiplication is always associative and it's always distributive. And what's nice about thinking of quaternions in terms of 4x4 matrices is that if you want to prove these, you just prove that you can represent quaternions in terms of matrices, and then prove the corresponding claim for matrices. Because we already know that matrix multiplication, when it's defined in the conventional way, is associative and it's distributive. That is, if I have three quaternions, q1, q2, q3, it doesn't matter if I do q1, q2 first, and then multiply on the right by q3, or if I do q2, q3 first, and then multiply on the left by q1, so it's associative. And for the distributive property, let's say I had q1 times the sum of q2, q3, that's equal to q1, q2 plus q1, q3. Now, just to emphasize that we cannot commute, let's suppose I had q2 plus q3, then multiplied by q1 on the right. Now, it's absolutely essential that when you distribute this, that you write it as q2, q1 plus q3, q1, that you keep these orders the same, that q2 is on the left, q1 is on the right. You can't just swap these like this because quaternion multiplication is not commutative. And furthermore, we can examine what the multiplicative identity and what the multiplicative inverses are. Now, the multiplicative identity is quite simple. Now that we're thinking of matrices, what's the multiplicative identity in terms of matrices? Well, it's just this matrix over here, where the ones are all along the diagonal here. This is the 4x4 identity matrix. And we know that when I multiply by this matrix on the left, or on the right, when I multiply that by any arbitrary quaternion, which is what I've written here and here, then I get the same thing back out. Now the question is, what quaternion does this matrix correspond to? Well, if I just look at the formula for the matrix representation of a quaternion, the A's are all along a diagonal, so A is going to be equal to 1. And then everything else, the B's, C's, and D's, are going to be equal to 0. So this is just this identity matrix is just the matrix representation of the quaternion 1, 0, 0, 0. So this is the multiplicative identity for quaternions. Very similar to complex numbers as well. We already discovered in the complex numbers that 1, 0 was a multiplicative identity. So we're seeing a lot of nice symmetries between the complex numbers and the quaternions. Now continuing with this matrix interpretation of quaternions, let's say I had some quaternion A, B, C, D, and I were interested in its multiplicative inverse. So if I have some quaternion A, B, C, D, the following, this is just that formula, would be the matrix representation of A, B, C, D. So what does it mean to find the multiplicative inverse of this matrix? So we're looking for the matrix such that when it's multiplied by this matrix, gives me the identity matrix. And this is the same thing as asking, what is the inverse of this 4x4 matrix? So if I can find the inverse of this matrix, that will be the inverse quaternion of A, B, C, D. And this matrix is quite remarkable when you actually take the inverse. For example, if you calculate the determinant of this matrix, you'll find that's actually a very, very nice quantity. And I won't spoil it for you if you want to actually compute what this determinant is. It's actually a very nice symmetric relation between A, B, C, and D. But when you invert this matrix, I'll give you the result of the computation. When you invert this matrix, you're going to find that, and when you convert it back to the 4-vector representation, you'll find that Q inverse is going to be A over the sum of squares of A, B, C, and D, minus B over the sum of squares, minus C over the sum of squares, and then minus D over the sum of squares. And notice again, this is very, very similar to what we're seeing with complex numbers in terms of taking inverses. And notice too, that if you haven't noticed this already when we're dealing with complex numbers, is that this sum of squares thing that we're seeing in the denominator is not at all arbitrary. Because we know that the squared length of Q is precisely the sum of squares, which means that the length of this quaternion is going to be the square root of the sum of squares of A, B, C, and D. So these denominators here are simply the sum of squares of the quaternion. And furthermore, for the complex numbers, if we had some complex number AB, its conjugate is going to be A minus B. We just negate that imaginary component. Now, since for quaternions we have 3 imaginary components, we're going to define the conjugate as A minus B minus C minus D. And also, it's very natural to define it in this way because when we define these 2 objects in this way, we can very nicely write Q inverse as this quantity, the conjugate of Q divided by the squared length of Q, just scaled down by the squared length of Q. And that's precisely what we have here. And notice that in the special case, when Q is of unit length, when Q has a length of 1, that means that the squared length is going to be 1. In that special case, where the quaternion is of unit length, the inverse and conjugate are the same thing. Now that we've set up the preliminaries behind quaternion calculations, we can now talk about why quaternions are interesting, in that they encode 3-dimensional rotations through any axis that we want and through any angle that we want. Now, the fundamental formula for quaternion rotations is the following, what I call the quaternion rotation formula, which says that if phi is some function, which I call phi sub q, this is going to be some rotation function associated with a quaternion q. And its input is going to be some vector v. The quaternion that comes out of that function is q, v, q inverse. And I make the additional restriction that this q, the associated quaternion, is a unit quaternion. That is, it's going to be of length 1. Now, since it's of length 1, instead of Q inverse, I could just as easily write QV Q bar, where Q bar is that conjugate. And now, when I want to rotate about some axis and about some angle, it's just a matter of picking which unit quaternion will do that job. So that's really what we're going to talk about for the next few minutes. And usually I like to motivate where formulas come from, just like I want to motivate where the Hamilton product really comes from, what the insight was behind it and what the derivation is. Unfortunately here, I can't really think of a good motivation for why the formula is this way. It certainly is the case that this formula does rotations, but I haven't really come up with a good motivation for it yet. But it turns out that this is going to be the rotation formula for quaternions. Now let's play around with this formula a little bit. Let's say I pick K as that unit quaternion, and I associate the following rotation function, phi sub k. And I'm going to input some vector v. So that means that the rotation formula is going to be kv k inverse. Now k inverse is just minus k, so the rotation formula is going to be minus k v k. And let's examine what that does to our coordinate system. Now let's use the physics interpretation of I, j, and k, where I is going to represent, first it's always going to represent 0, 1, 0, 0, but it's going to represent the x direction. J is going to be 0, 0, 1, 0, and that's going to represent the y direction. And then k is going to represent the z direction. So what we're going to do is we're going to apply this function, phi sub k, to each one of these basis quaternions. And then we're going to examine what the output of that operation is. That is to say, what are these three quantities phi sub k of I, phi sub k of j, and phi sub k of k? So you can imagine this as inputting the x-axis. So I is going to represent the x-axis in 3 dimensions. So we're wondering, what does this function do to the x-axis? And then here, this will correspond to, what does this function do to the y-axis? And then finally, what does this function do to the z-axis? So we're imagining not just rotating individual vectors, but rotating the entire coordinate system. And we're going to see what the output of these phis are going to be. So let's first compute phi sub k of I. So we just plug that into the rotation formula. So I get minus kik. Doesn't matter which way you do this in. You can do ki, that's going to be equal to j. So that becomes negative jk. Jk is equal to I. So I get negative I as a result of that. So that means that I, the unit x direction, gets sent to the negative x direction. Okay, that's our first result. Phi sub k of j, the unit y-axis, or the unit y direction, we just plugged into the formula. It's going to be negative k jk. And now I get kj is equal to minus I. So now I have ik. Then ik is equal to minus j. Because remember, ki is equal to j, so ik is going to be minus j. So what do I get here? I get j gets sent, or gets mapped to minus j. So that's pretty interesting so far. The x-axis gets sent to the negative x-axis. The y-axis gets sent to the negative y-axis. So what happens with k? So again, I just plug k into this formula, and what I'm going to get is negative k cubed. So k squared is minus 1, so I just get negative negative k, or just k. So that means that k is mapped to k, which means that the unit z direction is unchanged by this operator. So the z direction is the only axis which is not changed by this operator. And if you can visually think about what's going on here, the unit x-axis is getting rotated around to become the new minus x-axis. This j direction, the y direction, gets rotated 180 degrees around to its negative, but the k is preserved. So that means that we're rotating through the z-axis. Since if you can imagine rotating this entire coordinate system, rotating about the z-axis will preserve the z-axis. It won't change that z direction. So what is this operation phi sub k doing? Is rotating the entire coordinate system 180 degrees about the z-axis. So this is a pretty significant result. And I encourage you to visualize this, see what's going on with this phi sub k, and understand why this is a rotation as opposed to just being a reflection. We've taken care of a very simple rotation, one about the z-axis, 180 degrees. But what about more difficult rotations? This is really where the power of quaternions is going to be manifest, because even if you're very visually talented, if you can imagine these things in your head, it's, in a precise sense, it's very, very difficult to visualize the rotation of an entire coordinate system if you pick difficult enough axes. And it's actually very difficult to set up, even geometrically. So let me present how we're going to find the correct unit quaternion for rotating about some arbitrary axis, some arbitrary amount of degrees. So it turns out that if u is some unit vector in 3 dimensions, let me call it ux, uy, uz. For example, this might be 2, 2, 1, 1, 1, 1. We're actually going to use the example of 1, 1, 1 in a second. And it could be anything you want, some 3 vector. And it's a unit vector. And suppose I want to rotate about that axis theta degrees. It turns out that the correct unit quaternion to pick, q, is going to have the following 4 components. The first component, the scalar component, is going to be the cosine of theta over 2 degrees. The second component, the I component, is going to be that ux is going to be the x component of that axis vector multiplied by sine of theta over 2. And then the remaining components are similar. The j component is going to be u sub y multiplied by sine of theta over 2. And the fourth component, u sub z, is going to be multiplied by sine of theta over 2 as well. And in fact, if you pick a unit vector, if u is already a unit vector, that even when you multiply by these cosines and sines, then you're still going to produce a unit quaternion that you don't have to worry about checking the length anymore. And this will be clearer through an example. For example, let's consider the rotation about the 1, 1, 1 axis. So I imagine that vector in 3 dimensions, 1, 1, 1. That axis through 120 degrees. This is actually going to be a very interesting rotation. But you can see, if you're very visually talented, it's very, very difficult to imagine any arbitrary rotation through this axis in a very precise sense. Sure, you can imagine rotating a sphere, but if I asked you, can you estimate where such and such vector is going to be, that's actually a very difficult question. So this is why quaternions are extremely powerful. So we're going to rotate about 1, 1, 1. Now first, we notice that this is not a unit vector because the squared length is going to be 3, so its length is going to be square root of 3. So what we're going to do is first create the corresponding unit vector, u, just by scaling it back down by square root of 3. So we're going to consider the unit vector 1 over root 3, 1 over root 3, and 1 over root 3. Same direction, just scaled down. And now we're going to find the correct unit quaternion just by using this formula. So it's 120 degrees. So theta over 2 is going to be 60 degrees. So that means the first component is going to be the cosine of 60, which is 1/2. The second component is going to be 1 over root 3 times the sine of 60. So it's going to be 1 over root 3 times root 3 over 2. So it's going to be 1/2. And then the other ones are also 1/2. So it turns out that the quaternion, the unit quaternion we're going to select to do this job of rotating about 1, 1, 1 through 120 degrees is going to be the following quaternion: 1/2, 1/2, 1/2, 1/2. And now, what do? We just plug it in to the corresponding rotation function. We do that q, v, q inverse operation. So here I have q multiplying out on the left. I have some arbitrary input vector, let's say a, b, c, d. And then I multiply on the right by the conjugate, or the inverse of q. Now let me make a quick note about doing this sort of computation. In the previous example, I was considering rotating the entire coordinate system. I was considering rotating the x, y, and z directions. But let's say I was just interested in one particular vector to rotate. Let's say I wanted to do this operation, this precise rotation, with the vector, let's say, 1, 0, 0, which also happens to be the unit x direction. What I do for this quaternion, in terms of which quaternion I plug into this formula, I just plug in 0, 1, 0, 0. And this is why this is called the vector part, because when you put 3 dimensions into the 4th dimension, you just stick it into the vector part. So if I wanted to rotate 1, 0, 0 using this operation, I would just input the quaternion 0, 1, 0, 0, and then whatever comes out of that, I just look at the last 3 components, just the vector part, and you sort of ignore that scalar part. So this is how you would probably do this in practical applications. In terms of inputs and outputs, you're really only concerned with the vector part. And this will become clearer as we do the computations. As with the last example, we want to consider what this rotation does upon the entire coordinate system, not just individual vectors, but the entire coordinate system. So what we're going to do is just do precisely this computation, Q, V, Q inverse, or Q, V, Q bar. First, I'm going to consider what is phi sub q of I. What does this rotation do to the x-axis? And when we do these computations, this is really where we're going to see that matrix multiplication is really going to clean things up. So what I'm going to do is I want to first do this operation q times I. So how am I going to do this computation? I'm first going to create the 4x4 matrix corresponding to q. And to do that, you just plug it into that formula involving the A, B, C's, and D's as before. And it turns out that the 4x4 matrix corresponding to that quaternion 1 half, 1 half, 1 half, 1 half is the following 4x4 matrix. Now I want to know what quaternion results from doing Q times I. So I take that 4x4 matrix and I multiply on the right by a 4x1 vector, which is going to encode I. And that's precisely the vector 0, 1, 0, 0. And what I get out of that is some other quaternion, namely negative 1 half, 1 half, 1 half, negative 1 half. So that's just, and this is just ordinary matrix multiplication, which is why it's nice and clean. So when I multiply on the right by I, that's the same thing here as looking at the second column of this matrix. So that's why I get this as a result. So now I have the result of doing Q times I. But now I want to multiply on the right by Q inverse. So what I'm going to need to do is take this quaternion that I got out, convert it to its 4x4 matrix representative. Again, just plugging it into that formula, finding what matrix corresponds to this quaternion. And then I'm going to multiply on the right by Q inverse, represented as a 4-dimensional vector. Okay? So Q inverse, as this vector is going to be 1 half, and just negating the other 3, so I get negative 1 half, negative 1 half, negative 1 half. And on the left here, I have the 4x4 matrix corresponding to this intermediate quaternion here. And then I want to do this matrix times this vector. What do I get out of that? I get a very nice result, 0, 0, 1, 0. And what is that also known as 0, 0, 1, 0? That's precisely J. So this rotation takes the x-axis and rotates it to overlap with the y-axis. So I get sent to J. And if you continue doing this sort of computation, which I encourage you to practice with, what you're going to find is that phi sub q of J, the unit y direction, gets sent to K. And then K gets sent to I. So you can see that these axes are being shuffled around. They're being cycled around. I goes to J, J goes to K, and K goes to I. And this is actually a very, very nice rotation, just because it's cycling these axes around like this. And since I know what this rotation does to each of the basis vectors, I can now say what any arbitrary input vector will be outputted as. So let's say I have some quaternion, ABCD, that gets inputted to phi sub q. I can now say that the output of that is going to be, if the input is ABCD, the output is going to be Adbc. Now why is that? Because the x component right there, that B, is going to be sent to the y component. So that means that B is going to be placed right there in that y component, or the so-called J component. Now since J gets sent to K, that means the C is going to go over here in the Z component, or the K component, And then the k, that d, is going to go in that remaining slot. And the a is going to be unchanged. Now, going back to what I was saying before, suppose I were just interested in one particular vector in 3 dimensions. Let's say 1, 2, 3. In terms of quaternions, what I do is I input that as a quaternion, letting that first component be equal to 0. So I input that quaternion as 0, 1, 2, 3 into phi. And I just do the following flip-flopping of numbers here. And the output of that is going to be 0, the quaternion 0, 3, 1, 2. Now what that means is that if I take the vector 1, 2, 3, I do this entire operation, I rotate about 1, 1, 1, 120 degrees. The vector that comes out of that is the vector 3, 1, 2. Again, I'm just looking at those last 3 components. So this is the very, very nice result, that I can do these sorts of computations very quickly. Or I should say, the computations are very easily done once you develop the fundamentals behind doing this, and you've set up all this matrix arithmetic. Now let me close out this video by making a few historical notes and sort of talking about how quaternion math connects to modern vector operations. Now, we modern students of math and physics, when we learn about vector operations, the fundamental operations that we really learn about are the dot product and the cross product between vectors. Now, historically speaking, these operations come out of quaternion math. Quaternion math is really the more fundamental object. And in fact, quaternion multiplication can be defined in terms of dot product and cross products, or vice versa. You can define what a dot product and what a cross product is in terms of quaternion multiplication. And let me make that a bit clearer. Let's say we had 2 quaternions, Q1 and Q2. Now Q1, instead of writing this as a 4-component vector, I'm going to write it as an ordered pair, where this first one is going to be the scalar part. It's just the ordinary first component of the quaternion. And then this object V1 is going to be a 3-dimensional vector. So here I'm actually capturing, or I'm making it very explicit what I mean by scalar part and vector part. So in terms of quaternions, the first component is going to be W1, and then the remaining 3 components are going to be contained within V1. So this is just a different way of writing quaternions. And then similarly for Q2. And you can actually show that Q1 times Q2, where this is just the ordinary quaternion multiplication, can be written in the following way, in another very interesting way, that the new scalar part that you're going to get out of your quaternion, Q1, Q2, is going to be given by W1, W2, and this is just ordinary scalar multiplication, minus the dot product between V1 and V2. Remember, V1 and V2 are going to be themselves 3-dimensional vectors, so you then take the dot product between these two. And that whole thing becomes your new scalar component. And then your new vector component, those remaining 3 components, that's going to be given by the following. W1 times V2, so this is just scaling up a vector. It's just scaling up V2 by W1, plus W2 V1, so this is just scaling V1 by W2. And then you add another vector. You add the cross product between V1 and V2. And remember, the cross product is not commutative, so you have to make sure that when you're talking about Q1, Q2, that you have to write V1 cross V2. In fact, the cross product is anti-commutative. It's even better than quaternion multiplication in some sense. And I encourage you to verify that formula in terms of seeing that this is indeed the same as quaternion multiplication in terms of how we set it up in this video. Now notice in the special case where W1 and W2 are set equal to 0, which is kind of how they're normally done, where you're using quaternions in the setting of 3-dimensional space. You set W1 and W2 equal to 0, so Q1 is going to be equal to 0 V1, Q2 is going to be 0 V2, that when I do Q1, Q2, the output vector is pretty interesting. So every time I see a W1 or a W2, that goes to 0. So what I'm left with in the scalar part is the negative dot product of V1 and V2. And then when I examine the vector part, W1 and W2 are 0. So what I'm left with is the cross product between v1, and v2. So if you had two vectors in 3 dimensions, you could interpret those as two quaternions where the scalar part is set to 0, and then when you do q1 times q2, the thing that results is going to be, in the scalar part, is going to be the negative dot product between the two, and then the vector part is going to be the cross product between v1 and v2. So that's pretty interesting too. So I encourage you to play around with that if you're interested in that. Just to take an example of that, let's say, just precisely what I was saying, I had two vectors in 3 dimensions. Let's say v1 is 1, 1, 1, and v2 is 3, 2, 1. So I load those two up as quaternions. So now q1 is going to be, I'm going to put a 0 there, and then just write the vector part like that, 1, 1, 1. Now q2 is going to be 0, 3, 2, 1. Want to do ordinary quaternion multiplication, and you can do it my matrix way. You can do it the other way using that wacky formula. q1, q2 is going to be the following quaternion: -6, -1, 2, -1. So the scalar part is going to be -6, and the vector part is going to be -1, 2, -1. So what that means is that the dot product between v1 and v2 is 6. And you can see that that's quite obvious. 1 times 3 is 3, plus 2 plus 1, that gives me 6. So that makes sense. And what that means is that the cross product, v1 cross v2, is -1, 2, -1. And this is really historically where the cross product and dot product come from. So that'll wrap up this video. Hopefully you've enjoyed this discussion and this introduction to quaternions. And this video is a bit longer than my other ones, but I figured it's important to go over both the theoretical foundation and also the applied aspect of quaternions. Because if you do one or the other, then it's kind of, you're missing something. If you're doing just the applied stuff, if you're thinking like a physicist or an engineer, then you really don't know where this stuff is coming from. You really have no understanding of why this works at all. And if you do just the theoretical stuff, then, like a lot of other areas of pure math, you're left wondering, who gives a fuck? So hopefully you've enjoyed this video. Stay tuned for my other videos, and perhaps I'll do a whole series on quaternions, who knows. So thanks for watching.